So next, here in exercise 1B, we're being asked to calculate the average velocity associated with each of the ball drops. So the average velocity is going to be how far you go over how long it takes to go there. How far you go is what we measured, the distance dropped, over how long it took to go was 0.11 seconds. And they wanted in SI units. So SI units, we're almost there, right? Seconds is already the units of time in SI units. Centimeters is not the SI unit of distance. Meters is. So we just need to convert these, all these centimeters to units in meters. Over here I did it this kind of a fancy way for showing you how to use lock cells. I don't actually think this is super necessary. I'm going to show you another way to do it, and then we'll also get into the lock cells. We'll be using that when we go ahead and calculate the speed associated with those drops, average speed, average velocity, average speed. Here, average speed just means the size of the velocity, the magnitude. The velocity itself actually has a direction. We know that's straight down here because we're dropping it, but the speed is the size of that thing, how fast. Okay, so it has to calculate the speed associated with each of these drops, and they want it in SI units. So here we're going to we'll get our length, and we're going to put it in meters. And then I'm going to do that double click thing. Let's see, go over here, double click, makes it bigger. I could do what I did on that handout. I'm going to do it what I think is actually a cleaner way for this particular case. It doesn't really matter, but the whole point is how do you go from centimeters to meters? Well, what does that centa mean right there? In this case, that literally means 10 to the minus 2, or 1 over 100. So what I could do then is just go, to convert, I just go take this number, so that's, in that case that's 3.69, and divide by 100. And that's going to convert that to meters. Okay, and now to do it to all these, I'll just do shift click to the bottom, highlight, so I have the cell now that contains a formula in it, and I just want to fill all this down. Now to fill down, I was filling down before I was using the hotkey. If you don't know what that is, you could just go over here to where it says fill. It has all these choices. Fill, down, right, up, left. Here we want to fill down. And if you hover over that for a second, it shows you the hotkey for it. Fill down is Control D. So that's what I usually do here. Since I've got it here, I'll just click it and it'll fill down. But I could have done a Control D. That's what I did the first time, and I didn't mention what I was doing because I'm so used to doing it. Okay, so that's our length in meters. By the way, I could get the averages, these deltas, and everything for this converted bit in meters, for these converted lengths in meters, just by grabbing all these guys, highlighting over to the left here, selecting over to the left, and doing fill right. So you go over fill right, and you'll see the hotkey for that is Control R. So I'm just going to Control R it here. It fills to the right. So it just did all these calculations. Okay, I had to increase the decimal places on some of these because once you do this, once you convert to meters, to go out a few more decimal places to grab everything. So what do they want next? Let's look at it here. Next, they want us to get the velocities associated with each of those distances, right? So that's how far it fell in 0.11 seconds. So we assume the time's the same for every drop. Okay, and eventually they're going to ask us to report it in this form. But first let's get these speeds here. Units of meters per second. Okay, so the time of the drop, call that dt. I'm going to put that over here. You could put an equal signs on here. So often I don't, but I could put an equal sign there to show that I'm going to put the number associated with this symbol. This means the time, and that time was 0.11. And then I just want a number in here because I want to use this in calculation. So the units for it, I'm going to put over here, seconds. If I had put the units inside the cell with the number next to the number, I could have done that. I could have put S right here. But now Excel will not treat this as a number that I can use in calculations. It just treats it as text, which can't be used in calculations. So that's why I don't put the number there. I don't put the units there. I put them over here. Okay, now to calculate the speed. So speed is just how far you go, length divided by how long it took, time. So it's just going to be equal to, okay, so how far you go divided by how long it took you to go there. And that's in here. So that's 0.11 seconds. Just click on the cell that has it, click enter. Okay, and it just calculated it for me. So that's the speed associated with this drop. Now let's go ahead and we could fill this down. Remember, Control D fills down. I could go over here to fill, right, and click fill down, but I'm not going to do that. I just got this. I'm just going to use Control D. That's the hotkey for it. And oh, what's this happen? Mistake. Divide by 0. What just happened? Okay, let's look at the pattern. Okay, so here it took C2 divided by J3. So here's C2 divided by J3. J3 is over here. Okay, so that's exactly what we wanted. What happened in this next one? Now it was C3, so it goes down to this one and then divides by the next cell down below that one. But notice the next cell down below that one has nothing in it, so it treats that as 0. So let's divide by 0. That's not what we wanted, right? We wanted each one of these, we want each of these to be divided by this. So how can I save this? I could put 0.11s filling down here. That would be one way to do it, but I don't want to do it that way. There's a cleaner way to do it, and that's with lock cells. So the way you lock cells is you use this $sign. So the $sign just locked J. So that means it locked on the column. And then I put that right in front of the J. Then I go over here and put a $sign right in front of the 3. I had to sneak it in there. So now that locked on the row. It locked on, so it's locked on column J, row 3. Now it's locked completely on that cell. Now watch what happens when I fill this pattern down. I get the desired result. To a lot of sig figs, maybe I'll decrease my decimal places here. Didn't have to right there. Maybe that's like an intermediary calculation. Let's see what they want next here. Use fill right to quickly calculate the experimental average, velocity, and uncertainty, which is the standard error, and then so we can report that result in the form velocity is equal to our best guess on the velocity plus or minus our uncertainty, and report this result. If you're doing it online, then the spreadsheet reports the result, but if you're doing it with a lab handout or you have a lab manual, you'd want to actually write out the results here on this piece of paper or in your lab report book if you were doing it doing a lab report. Okay, so what do we do to do that? Well, the hint is I actually started it over here. If I fill right, it just fills this pattern over, fill to the right. Okay, that was the speed. So this is the average speed associated with these drops in meters per second. And here's the delta based on the way we did it before. There's a standard error. So how would we report our answer? We would report our answer as 0.3344 plus or minus 0.0004 meters per second. If I want to report my answer including uncertainty in Excel, a pretty nice way to do it would be like this. Just go V is equal to, and then over here I'm gonna put the answer. Well, actually, let's see. Yeah, I'll do it that way. So V is equal to. I'll put the answer over here. Anyway, so we can see what the answer is. It's my best guess, which would be the average, which is right over there. So that's point. I'm just gonna type it in by hand here. 0.3344, and then now it's plus or minus. There's different ways I could make a notation for that, but a nice way to get it would be, let's see, so if we're at the Home tab, we go to Insert, then over here, so we got this option for symbol, and then let's see, they got it here in the symbols. Here it is, plus or minus. Insert it, plus or minus, close that one, and then it's this guy up here, 0.0004, and the units are meters per second. I might as well put the units here in this case because I couldn't use this thing in a calculation anyway. It's it's got this plus minus thing. Excel wouldn't know what to do with it. But anyway, that's how we would report the final answer. Maybe I could reformat this to align it to the left over there so you can see what's going on. So V for speed is equal to, or V for velocity is equal to that. It's our mean plus or minus our uncertainty. We're ready to go on to exercise 2 now in the handout. If you're doing this online, what I'd like you to do is go ahead and label everything. Here I just started doing this, and this was actually all exercise 1. And there's the final answer. Well, these are all the final answers to exercise 1, but here's the final answer to the velocity with the uncertainty that we calculated from over here. Okay, so I want to label exercise 1. What shall I do? I'm going to want to insert a row over here because I don't have any room for it. So I'll go over here to insert rows. Okay, great. I can insert a row and then now label this. Made it bold and underline. Okay, ready to start exercise 2. All right. So there's our data for exercise 2. One question here is asking, what is the rule of thumb uncertainty for each of these data points? I'll call it rod X for rule of thumb uncertainty for each of these data points. Okay, well, if you think about that for a second, the rule of thumb uncertainty says that it's 1/2 the least tick. What's the least tick? The least tick would be 0.01. So here I could just use Excel to calculate it. I could go rod X is equal to 0.01, because these go to the 0.01 decimal place, and then divide by 2. Then we put enter to evaluate that, and then centimeters is the units. So we just answered the first question. What is the rule of thumb uncertainty? Okay, we calculated the rule of thumb uncertainty. Now it's asking us to find the standard deviation, and from that get the standard error for each of these length, width, and thicknesses that we have for this block. So this is some block that we measured, and supposedly we measured it, but this is the data we got from measuring this block. So what is the length, width, and thickness uncertainty using standard deviation and standard error? So now we know how to calculate that. Standard deviation, we just go equals to, see it, SDVA, and standard error is equal to standard deviation, which we just calculated, divided by the square root of the number of data points. Here the number of data points is 5. So that's the standard error. So now we get them all just fill right. Just grab that. So these are the cells that have the formula in it. Fill right everywhere you want that. So it's going to do the same thing for each one of these values. Fill right. So now here's the standard deviation for the width. Here's the standard deviation for the thickness. Here's the standard error for the length, standard error for the width, standard error for the thickness. Okay, so all those are calculated for us. Oh, and we also wanted to calculate the average. Just insert a cell right here. I don't want a cell. Insert rows. Okay, so I inserted a row right there. Put the average right here. The same way. And calculate it. Start typing it. Double click when you see the formula you want. Double click on it. And here I don't even need to close that parentheses. Fill to the right. Okay, so there's the average length, average width, average thickness. And now we can report just like it's asking for. So we'll call report like this. L equals width equals thickness equals. Over here it's going to be, we're just going to type it longhand. Best guess is the average and insert plus or minus, and the standard error on the length, 0.01. Round to 1 sig fig for uncertainty. Just read the uncertainty right here from the standard error, and then I rounded it myself to 1 sig fig. Last thickness. And the units on all these, centimeters. Notice I can just put the units once here and it stands for all of them. In fact, in this case I can see what the units are and what everything is from over here. So in that case, technically maybe I didn't even need to include the units, but I felt like it was a good idea to put it on this one over here, and then this centimeters counts for everything. Everything is in units of centimeters. So another question is here, standard error or rule of thumb. And I'm going to go ahead and let you answer that. You can think about it. That's a question for you. Just put your answer here. I think, or my answer and then however you want to type it. So put your answer in there if you're online. If you're doing it in the lab with a lab handout, then you can just write down your answer on the piece of paper. Okay, now we want to calculate the volume for each of these blocks. For each of so each of these measurements of the block. So this is the same block. These are all measurements for the block. So we have one block, we measure 5 times the length, the width, and the thickness of the same block. Maybe we have a different student, or we'd make the measurement on different parts of the block. So we get kind of a spread, and then we get an average here. Then we can get our average. And since we have 5 or more data points, we have a quorum for statistical analysis. So when you have 5 or more data points, you can go ahead and use statistical methods to calculate the uncertainty. And that's just calculating the standard deviation and from it the standard error, like we did. Now to get the volume, units of centimeters cubed. I'm just going to do, right there, I'm just going to do caret 3. Okay, here's, if you want to be fancier, you can just highlight this, and then we can go to font, where there's more here, and then it's got superscript, and then it's units cubed. That looks a little better, but caret 3 was fine. I usually use just caret 3 because I don't want to spend so much time formatting stuff. But we did that, so that's good. Okay, so how do I calculate the volume? Volume is equal to length times width times thickness. Okay, so that's the volume, and then to calculate it for all of them, all these associated with all these measurements, just fill down. Again, Control D. Or you could go use that fill thing, but just Control D does it good. And there's even other ways you can do it. So that's the volume associated with each of these different measurements of the same block. So we could get the average volume and our uncertainty on the volume all right here. Just so the formula's in here, just fill right. And that's it. So it's saying report the volume and its uncertainty. Here, notice there's a lot of decimal places. Let's see what I get if I decrease. I'm liking on that. So for this case, the volume equal to, we'll put the answer over here. We can see, okay, so if that's the amount of uncertainty is 1 cubic centimeter, then that really shows what the amount of sig figs we could have in this, right? That 1 is going to be kicking on the door of the ones place. So technically, to be right about this, I should round this up to the nearest ones place over here. So what I'm saying is, put it in this way. Okay, I put it caret 3, that means cubic centimeters. Again, we could have used the superscript for that, but I'm just going to leave it like that because I think it's fine. Now it's time for exercise 3. So I'm going to use this data to do the example for exercise 3. But remember, the exercise is saying, okay, you can follow along with me, where I'll use this data on the spreadsheet, but you want to use the data in the handout. So here's exercise 3. You want to use this data. Do the same thing, but with this data. And it's kind of similar data, so the results will be kind of similar. So you can just follow along, so that all the calculations and methods will be the same. The only thing that's different, slightly different, is you use this data instead. All right, but now with this data, we're going to go ahead and do the exercise. So let's see what it's asking for. Calculate the volume. Now the volume of a ball, we could model as a sphere. Balls are spherical. So the volume of a sphere is 4/3 pi r cubed. So we're going to use Excel for that. So it's going to be, okay, so 4/3, but it's pi, on top is pi. So Excel actually has a formula for pi. So it's times. Excel needs to know everything. It needs to know that you're going to multiply. So 4 times, and then pi. When I find the function, there's a function for pi. I just double click on it, and I have to close parentheses for that. I've never tried to use the pi function with arguments, but anyway, when you just have it like that, pi open close parentheses, it returns the standard value of pi. So that's 4 pi. Now it's going to be times the radius cubed. Now here we're given the diameter, and the diameter is twice the radius. It's much easier to measure the diameter of a ball than the radius. If you're given a ball and you're asked to measure it, you're going to just automatically measure the diameter, but then the radius is just half of that. So Here I did open paren, you're going to see why in a second. So I click the value where the diameter is, and then to get the radius, I just divide by, not 3, but 2. And then now I have to cube that guy. Okay, and then it's 4/3, so there's a division by 3. Overall divide by 3 for that. Okay, and then we just fill this down and calculates the volume for each of these diameters. Ball 1, 2, 3, 4, 5. Again, that's a kind of an embarrassing amount of sig figs, so maybe I'll just reduce them a few. Oh, not that way. Anyhow, now it's asking us to calculate the density of each ball. Okay, so density is just the mass divided by volume. That's the definition of density. We'll do density, and here looks like I can just go ahead with units of grams per centimeter cubed. Is that SI units for density? No, not exactly. SI units would be kilograms per cubic meter, but that's actually quite a convenient unit. It's a metric unit for density. Grams per cubic centimeter. Cubic centimeters are actually equivalent to milliliters, so grams per milliliter is a very common unit for density. For example, for the density of water is 1 gram per milliliter, 1 gram per cubic centimeter, and it's quite common in chemistry and just anywhere it's convenient. So here we want to calculate it. It's equal to the mass in grams divided by the volume in cubic centimeters. There's our density. And I decreased everything to 3 sig figs. I can see over here I got 3 sig figs at the most on my data. I mean, that one's got 2, but anyway. 3 sig figs seems to be just about as much as we can expect, so I decreased everything to 3. And again, I'm not sure if it's rounded properly, but you know, whatever. This is the answer. Okay, we just calculated the density in grams per cubic centimeter of our balls. So here's ball 1 through 5, and they're pretty much the same kind of ball, and they pretty much have the same kind of density. So this first one's a little different. Now they're asking us to get that in SI units. So these are metric units, grams per cubic centimeter, which is like grams per milliliter. But that's not SI units. So if we want the density in SI units, it would be density in SI units would be density in terms of kilograms per cubic meter. Kilograms is the SI unit of mass. Cubic meter is SI unit of volume. There's a couple ways we could do this. One way would be to just convert, let's see, to calculate these volumes, we could first convert these diameters in centimeters to meters. And then when we did the calculation of volume, it would give us the volume in cubic meters. That would be one way to go. That's not bad. And then, so like maybe we could add, I could add a new row here if I wanted. Like go over here, insert row. I don't know. But then that would insert a row into these. I don't want to do that, but I could go over here. I can do diameter in meters. And then go, that's equal to, I want to convert these into meters, so I would just take this, divide by 100, fill down. Okay, and then go ahead and calculate the volume the same way I did before, but using the diameter in meters. I'm just going to call this volume. And so when I auto-formatted that, it auto-formatted to this cell, which had all this stuff in it, but that's displaying just fine across overriding all these other cells. So I just did it by hand to get it like that. Volume in cubic meters. That's going to be equal to same thing as before. Diameter. That's in meters now. Over 2. Diameter in meters over 2, divide by 3, 4/3 pi r cubed, to cube that. So those volumes are pretty small in cubic meters. I'm also going to do the mass. and put the mass in there. So to convert the masses to kilograms, divide by 1,000. Grams divided by 1,000, go to kilograms. Move this down. And now our densities get the same way as before. Here in kilograms per meter cubed, it's going to be equal to mass divided by volume. Yeah, I reduced the number of sig figs. I mean, legit, what's the most we should have? 2 sig figs. I'm just playing to that many here. Feels fine to me. Okay, so what are they going to ask us next? Yeah, we're going to need to find the standard error for this. We're going to finally want to express this in this following form. Get the answer over here. I'm going to want to express it like this. My density equals rho is the typical symbol for density. So to get it on the spreadsheet here, I'm going to go insert symbol. There it is, rho. Rho is the density. So it's going to be equal to, well, okay, I still have to calculate the average and standard deviation and standard error to write it down here. I think I'm going to need a few more spaces for that. So I'll move that down there. Just get it out of the way. Okay, I can calculate everything for everything at once. Oh, and by the way, just FYI, I'll put it over here that 1 gram per milliliter, which is a cubic centimeter, that is equal to 10 to the 3, that is 1,000 kilograms per meter cubed. So we could have used that to get the density over here, right? Actually, I'll just repeat this, just FYI. And I'll get that same density by using this conversion factor. So let's see how I would use that. So I want to get this one on top. So kilograms per cubic meter would go on top of the conversion. This is essentially make my magic 1, right? So multiply by this and divide by this. These have, and on the density that has units of, there's the density. And so I want to convert these densities here in grams per cubic centimeters to these densities here. So what's the procedure? So it's going to be equal to this, and then now here's how the conversion factor works. 10 to the 3 kilograms per meter cubed is on top, and then 1 gram per cubic meter would be on the bottom. And so on the bottom, the grams per cubic meter will cancel with that grams per cubic meter, and you'd be left over with units of kilograms per meter cubed. But to get that, you had to multiply everything by 10 to the 3. So that's how that would work. So it would be times 10 raised to the 3. And you can see you go right here, and we get the same thing as we had over there. Okay, so it just goes to show a lot of times there's a bunch of ways to do these things. It's the same thing. Now, calculate the average and standard error. Okay, so double click it, drag select, enter, calculate standard deviation, CVA, get it. This one is standard deviation divided by square root number of data points, again is 5. Got that? Now just fill right. Get everything at once. Fill right. Okay, and so here's my answer. I'm going to, so there's my, I'll take my final answer over here. Doesn't matter which one I use. And by the way, if you're doing this online or in the lab, I'm not expecting you to have this extra column right here. So you know what, maybe I'll just get rid of it. I'll just delete it right now so you're not confused. Don't even need it, right? That was just another way I could have done this conversion. And in fact, that way would have been better because then I wouldn't have needed to make these extra columns right here like I did. But anyway, already did it. So these guys right here, I'm going to go ahead and reduce I'm going to round those up. Let's see. Uncertainty should really only have one sig fig to it. So how would I express this? So it's going to be 1,000 plus or minus 60. I could have the O2, but this is really showing me I only have 2 sig figs, right? Which, does that make sense in the data? Well, let's see. The smallest one here in the data had 2 sig figs. And this is the uncertainty associated with our density measurements. So how could I write this? Really, this would be best expressed as and here maybe I'll be fancy. Highlight that. Go to superscript. Just was fancy on that last one. So it's 1,000 plus or minus 60 kilograms per meter cubed. How I'd write that. Okay, I think we're done with this lab now. Let's see. Yes, we are done with the lab. So you can just do the same thing, but remember, don't use this data. I mean, you could try it with this data, but then once you're done with that, you want to go ahead and put in that other data. In fact, if you were to go and get the data you're supposed to use, this data right here, and just overwrite that into these fields right here, it would just update all the calculations for you. And so now if you have something went wackadoodly over here. Oh, I must have done something. Oh, I deleted a row. Okay. Yeah, and this row got deleted to 0.11. And so over here, that should have been divided by that. Lock it. That. So I ended up clobbering something. But there I just fixed it, and that was seconds. Okay. So we're all done. Do your best to enjoy it, and we'll catch you on the next exercise, the next laboratory.